Maneuvering into Lunar Orbit, detailed breakdown of Resilience's $5 million navigation system. Introduction. The Resilience navigation system represents a cutting-edge approach to achieving successful lunar orbit insertion and stabilization with a projected budget of $5 million. This initiative encompasses a comprehensive set of maneuvers and calibrations designed to ensure precise control of the spacecraft as it transitions from Earth to a stable orbit around the Moon. The entire operation is divided into 5 distinct phases, each critical to the mission's success, taking place from Q1 2023 through Q4 2024. Phase Breakdown. 1. Initial trajectory calculations, Q1 2023. The journey begins with the Resilience navigation system being launched into space. At this stage, engineers and scientists focus on calculating the spacecraft's initial trajectory. This involves leveraging complex algorithms and simulations to predict the spacecraft's path based on its launch parameters, orbital mechanics, and gravitational influences from both the Earth and the Moon. Real-time data from the spacecraft's sensors and communication with ground stations play a vital role in ensuring these calculations are as accurate as possible. 2. Mid-course corrections, Q2 2023. Once the spacecraft is in transit, mid-course corrections are necessary to refine its trajectory. This phase involves executing small thruster burns to adjust the spacecraft's path based on actual flight data. Engineers analyze the spacecraft's position, speed, and trajectory in real time, making adjustments to account for any deviations from the planned path. The calibration of the thrusters is critical during this phase, as precise control is required to make these adjustments effectively. 3. Pre-insertion burns, Q3 2024. As the spacecraft approaches the Moon, pre-insertion burns are conducted to prepare for the critical insertion into lunar orbit. This phase requires significant planning and execution, as the spacecraft must be positioned correctly to enter the Moon's gravitational influence at the right speed and angle. Engineers conduct rigorous simulations and tests to ensure that the thrusters can operate under the expected conditions. The pre-insertion burns are designed to slow the spacecraft down and align it with the desired orbital path. 4. Insertion maneuvers, Q4 2024. The insertion maneuvers are the climax of the mission, where the spacecraft executes the final burns needed to enter and stabilize in lunar orbit. This phase requires extreme precision, as any miscalculation could result in the spacecraft missing its target orbit or entering an unstable trajectory. The navigation system employs advanced algorithms to calculate the necessary thrust and timing for these burns, ensuring that the spacecraft can transition smoothly into its designated orbit around the Moon. 5. Stabilization adjustments, end of Q4 2024. Once the spacecraft is in lunar orbit, stabilization adjustments are made to maintain the desired orbit. This involves continuous monitoring and minor thruster burns to counteract any perturbations caused by the Moon's uneven gravitational field or other factors. The navigation system continuously processes data to ensure that the spacecraft remains on its intended path, adjusting as necessary to maintain stability. Technology and calibration. The Resilience navigation system's success relies heavily on the integration of sophisticated technologies. The thruster calibration process is particularly crucial, as it ensures that each thruster responds accurately to commands. Engineers conduct extensive testing to validate the performance of the thrusters under various conditions, simulating the environment in which they will operate. This involves measuring thrust output, response time, and precision of control, allowing for fine-tuning before the actual maneuvers are executed. Conclusion. The maneuvering into lunar orbit using the Resilience navigation system showcases a comprehensive and structured approach to space exploration. By dividing the process into 5 critical phases, the mission encapsulates a blend of advanced technology, rigorous testing, and meticulous planning. As the project progresses from initial launch in Q1 2023 to anticipated lunar orbit stabilization in Q4 2024, it exemplifies the collaborative efforts of engineers, scientists, and mission planners in achieving a complex and ambitious goal. The success of this mission will pave the way for future exploration and potential human presence on the Moon, marking a significant milestone in humanity's quest to explore outer space. The content provided outlines the maneuvering into lunar orbit with the Resilience navigation system, detailing its trajectory adjustments and thruster calibration phases from Q1 2023 to Q4 2024. Some counterintuitive aspects can be derived from the information presented. 1. Complexity versus budget. It's surprising that a $5 million budget can support the intricate technology required for lunar orbit maneuvering. Typically, space missions demand significantly higher funding, often running into hundreds of millions or even billions. This indicates that the Resilience project may be leveraging innovative, cost-effective solutions or existing technologies to achieve its objectives, which is counterintuitive given the traditional expectations of space mission costs. 2. Phased approach. The structured 5-phase approach may seem overly cautious given the urgency typically associated with space missions. However, this meticulous planning allows for incremental validation of each step, ensuring that potential issues can be addressed before progressing. The counterintuitive aspect here is that in high-stakes environments, a slower phased approach can yield higher success rates than rushing through phases. Contrary to the common belief that speed is paramount in mission execution. 3. Real-time data processing. The reliance on real-time data processing for trajectory adjustments might seem impractical given the vast distances and potential communication delays with lunar missions. This could lead one to believe that pre-calculated trajectories would be more reliable. Yet the ability to adaptively correct based on real-time data demonstrates a shift in how space navigation is approached, emphasizing flexibility and responsiveness over rigid planning. 4. Thruster calibration precision. The emphasis on thruster calibration for maneuvering might seem excessive, especially given that thrusters are often assumed to be reliable once tested. This focus on precision indicates a deeper understanding of the complexities of thruster dynamics in varying gravitational fields, which challenges the notion that once a system is calibrated, it does not require ongoing adjustments. 5. Divergence in source information. The mention of discrepancies in technical details across different sources highlights the counterintuitive idea that consensus in technical fields can be elusive. One might expect uniformity in reporting on such a structured project, but the variance suggests that different stakeholders may prioritize aspects of the project based on their specific interests or expertise, showcasing the multifaceted nature of aerospace technology that defies simplistic narratives. These points illustrate that the Resilience project embodies a blend of innovative thinking, meticulous planning, and adaptive strategies that challenge common assumptions about space exploration and budget constraints. The report on the Resilience navigation system for lunar orbit maneuvering contains several significant details that may be overlooked by many readers. Here are the crucial aspects and their significance. 1. 5 phases of trajectory adjustments. The report outlines 5 distinct phases in the trajectory adjustment process, which are pivotal for the spacecraft's successful insertion into lunar orbit. Initial trajectory calculations. This phase involves determining the launch trajectory based on the spacecraft's initial parameters and the gravitational influences from Earth and the Moon. The importance of this phase lies in its foundational role. Inaccuracies here can lead to catastrophic mission failure. Mid-course corrections. These adjustments are made using real-time data to refine the spacecraft's path. Many readers might underestimate the importance of real-time adaptability in space missions. The ability to respond to unexpected variations in gravitational forces or spacecraft performance is critical for mission success. Pre-insertion burns and insertion maneuvers. These phases are where the spacecraft executes planned burns to enter lunar orbit. The significance here is that these maneuvers require precise timing and fuel management. The intricacies of fuel allocation and the timing of burns may not seem compelling at a glance but are vital factors that can determine mission success or failure. Stabilization adjustments after the insertion. The spacecraft must stabilize its orbit. This phase often gets less attention because it occurs after the major maneuvers are complete. However, stabilization is crucial for the operational phase of the mission as it affects the spacecraft's ability to conduct scientific observations or relay communications. 2. Thruster calibration and its importance. Thruster calibration is a technical detail often overlooked in discussions about navigation systems. Precision requirements. Calibration ensures that thrusters respond accurately to control inputs. Any miscalibration can lead to trajectory deviations, rendering the spacecraft unable to achieve its orbital goals. Understanding the exacting nature of this process highlights the challenges engineers face in ensuring reliability in hostile environments. Testing and validation. The extensive testing involved in ensuring that thrusters operate correctly is significant because it underscores the rigorous engineering practices required for space missions. Many may not appreciate the level of validation needed to ensure functionality under varying conditions. 3. Integration of information from different sources. The report indicates that while the core information remains consistent across various sources, the depth and focus can vary significantly. Diverse perspectives. Some sources might emphasize software algorithms while others focus on hardware specifications. This variance is significant because it illustrates the interdisciplinary nature of space missions, where software and hardware must work in harmony. Disregarding one aspect over the other can lead to a skewed understanding of the mission's complexities. 4. Timeline and its implications. The detailed timeline from Q1 2023 to Q4 2024 provides insights into mission planning that many might take for granted. Project management. The timeline reflects the meticulous planning required in aerospace projects. Each phase builds on the previous one, and delays or issues in one phase can have cascading effects. Understanding this can enhance appreciation for the logistical and strategic elements of space missions. Future missions. The experience gained from this timeline may inform future lunar missions or even missions to other celestial bodies. The lessons learned regarding trajectory management and thruster calibration can lead to improved designs and processes, which is a significant takeaway for long-term space exploration strategies. 5. Significance of technological advancement. While the report highlights a $5 million budget, the implications of the Resilience navigation system extend beyond financial considerations. Technological innovation. The development of this navigation system represents a stride in aerospace technology, showcasing how advancements in algorithms and real-time data processing can enhance mission outcomes. The significance here lies in the potential for these technologies to be adapted for other applications beyond lunar missions. Collaboration across disciplines. The project exemplifies the integration of various engineering disciplines from software development to aerospace engineering. This collaborative approach is essential for tackling the complexities of modern space exploration, a detail that might not resonate with readers focused solely on technical specifications. Conclusion. The Resilience Navigation Systems report encapsulates a wealth of information that is critical for understanding the complexities of maneuvering into lunar orbit. By focusing on often overlooked details such as trajectory phases, thruster calibration, and project timelines, readers can gain a deeper appreciation for the technical and strategic intricacies involved in such missions. Recognizing the significance of these elements is vital for enthusiasts, professionals, and policymakers alike as they shape the future of space exploration. 1. Phases of trajectory adjustments. The Resilience navigation system employs a structured approach consisting of 5 phases for trajectory adjustments crucial for lunar orbit insertion. These phases include initial trajectory calculations, post-launch mid-course corrections, pre-insertion burns, insertion maneuvers, and stabilization adjustments. Each phase is meticulously planned to navigate the complex gravitational influences of both Earth and the Moon, ensuring that the spacecraft can achieve and maintain its intended orbit around the Moon. 2. Thruster calibration. The calibration of thrusters is vital for executing precise maneuvers. The resilience system focuses on extensive testing and validation processes to ensure the thrusters respond accurately to commands for fine-tuning the spacecraft's trajectory. This meticulous calibration is essential for the successful execution of the planned trajectory adjustments and is a critical component of the overall navigation strategy. 3. Integration of advanced algorithms. The Resilience Navigation System leverages advanced algorithms and real-time data processing to ensure precise orbital insertion and maintenance. This integration of sophisticated software solutions allows for rapid adjustments based on real-time telemetry, enhancing the spacecraft's ability to respond to dynamic conditions during its journey to lunar orbit. The reliance on high-level computational techniques underscores the complexity and modernity of the navigation system. For project timeline and milestones, the project timeline spanning from Q1 2023 to Q4 2024 outlines significant milestones in the development and operation of the Resilience Navigation System. Key events include the launch of the navigation system, execution of mid-course corrections, pre-insertion burns, and final insertion maneuvers. This structured timeline not only illustrates the phases of maneuvers but also emphasizes the importance of each phase in achieving successful stabilization in lunar orbit by the end of 2024. 1. Apollo 11 Lunar Orbit Insertion 1969. The Apollo 11 mission, which marked the first manned landing on the Moon, involved a critical maneuver for lunar orbit insertion. After launching from Earth, the spacecraft executed a series of burns and trajectory adjustments to ensure it entered a stable orbit around the Moon. The lunar module Eagle separated from the command module and descended to the Moon's surface utilizing precision navigation and thruster calibration for a safe landing. 2. Lunar Reconnaissance Orbiter (LRO) Orbital Insertion 2009. NASA's Lunar Reconnaissance Orbiter was launched to map the Moon's surface in detail. After its launch, LRO underwent a series of trajectory adjustments and calibration maneuvers to achieve its intended orbit. The spacecraft performed mid-course corrections and insertion burns to navigate through the Earth-Moon system, eventually achieving a polar orbit around the Moon. This mission showcased advanced navigation systems and thruster technologies for precise orbital insertion. 3. Chandrayaan-2 Lunar Orbit Insertion 2019. The Indian Space Research Organization's Chandrayaan-2 mission included a complex lunar orbit insertion phase. Following its launch, the spacecraft executed multiple trajectory adjustments and precisely calibrated thruster burns to align its path for a stable orbit around the Moon. The mission faced challenges during the landing attempt, but the orbital phase successfully demonstrated India's capabilities in lunar navigation and maneuvering, highlighting the importance of accurate thruster calibration and trajectory management. Future outlook: predictions for lunar navigation systems and space exploration. As we look toward the future of lunar exploration and the advancements in navigation systems like the Resilience Project, several key trends and predictions can be made regarding technological improvements, mission strategies, and the broader implications for space exploration. 1. Advancements in navigation technology. The Resilience Navigation System serves as a benchmark for future projects, showcasing the integration of sophisticated algorithms and real-time data processing. Predictions indicate that by 2025, we will see the emergence of more autonomous navigation systems equipped with artificial intelligence (AI) capabilities. These systems will be able to make real-time adjustments to trajectories without human intervention, significantly enhancing mission efficiency and safety. 2. Increased collaboration and data sharing. As lunar missions become more frequent, collaboration among space agencies, private companies, and international organizations will likely increase. Data sharing platforms will emerge to facilitate the exchange of information regarding orbital mechanics, navigation techniques, and best practices. This collaborative environment will accelerate the development of navigation systems and enhance mission planning, paving the way for more ambitious projects. 3. Enhanced thruster technologies. The calibration of thrusters is crucial for precise maneuvers, and future developments will focus on creating more efficient and responsive propulsion systems. Innovations such as electric propulsion and advanced chemical thrusters will allow for finer control over a spacecraft's trajectory. By 2026, we may see thrusters capable of performing multiple functions, reducing the need for different systems and streamlining spacecraft design for extended mission durations and complex trajectories. With the successful implementation of the Resilience Navigation System, future lunar missions will likely involve longer durations and more complex trajectories, including missions to the lunar poles and beyond. Advanced navigation systems will need to handle varying gravitational influences and solar radiation effects, leading to the development of new algorithms that can adapt to changing conditions. 5. Integration of lunar infrastructure. As plans for lunar bases and sustainable human presence on the Moon, advanced navigation systems will need to adapt to support infrastructure development. This includes precise landings for rovers and habitats. By 2027, we can expect navigation systems to incorporate 3D mapping technology and utilize data from lunar orbiters to enhance landing accuracy and operational planning. 6. Commercialization of lunar exploration. The rise of private companies in space exploration will drive competition and innovation in lunar navigation systems. By 2028, we may see the commercialization of lunar resources, necessitating robust navigation systems capable of supporting mining operations and transportation logistics. This shift will create demand for navigation technologies that can operate in a commercial context, leading to further advancements. 7. Interplanetary navigation systems. As lunar exploration progresses, attention will shift to Mars and beyond. The technologies developed for the Resilience system will lay the groundwork for interplanetary navigation systems. By 2030, we can anticipate the adaptation of similar trajectory adjustment and thruster calibration methods for missions to Mars, enabling more complex interplanetary journeys. 8. Sustainability and environmental considerations. Future navigation systems will increasingly focus on sustainability. As space agencies and private companies become more aware of the environmental impact of space exploration, the design and operation of navigation systems will prioritize energy efficiency and reduced space debris. By 2031, we may see navigation systems that are designed to minimize fuel consumption and optimize trajectories for environmental stewardship. 9. Human factors and cognitive assistance. As missions become more complex and involve longer durations, the role of human operators will evolve. Future navigation systems will incorporate cognitive assistance technologies to support astronauts during critical maneuvers, offering real-time suggestions based on data analysis. This trend will help reduce cognitive load and enhance decision-making capabilities for crewed missions. 10. Public engagement and education. The excitement surrounding lunar exploration will drive public interest and education initiatives. By 2032, we will likely see an increase in educational programs focused on space navigation, encouraging the next generation of scientists and engineers. The success of navigation systems like Resilience will serve as a case study in educational curricula, inspiring innovation and interest in space exploration. Conclusion. The future of lunar navigation and exploration is bright, with numerous advancements on the horizon. As we move towards more sophisticated systems, collaborative efforts, and sustainable practices, the lessons learned from the Resilience navigation system will serve as a cornerstone for future missions. The interplay of technology, collaboration, and public engagement will shape the next chapter of space exploration, paving the way for a deeper understanding of our universe.